Am I audible? All right, let's start in a few minutes. Is the screen visible clearly?
Yes, sir.
Okay, let's get started. We'll be discussing some of, we'll be continuing from the last session where I think the last thing that was discussed was critical points of a multivariable function and then global extrema on bounded domains for continuous functions. So in that session, I think you've seen a procedure to find out the critical points of, say, two variable function within a triangular region and then computing by hand. You're considering all the boundary points and all the critical points and then listing them down in a table and then comparing with each other to see whether you have maxima or minima. But here we'll see something which is which mimics in some sense the tests that you have in the one-dimensional case. In the one-dimensional case, you have a second derivative test for local minima and maxima, right? So if your second derivative is negative, then it's a maxima. It's if it's positive, then it's a minima, and if it is zero, then it is inconclusive. We'll have something similar over here. But before we get into that, what even is the version of second order derivative? That is what we'll discuss first. And then we'll see all of these second order tests for two variable functions and three variable functions. And you'll see that with each added dimension, the complexity increases. So that these are the only two cases that we'll describe. And then this last section, an interpretation of the second order test, is something that is not exactly a part of this course, but I just wanted to say it so that you get a better intuitive idea of what is happening. So let's get started with it. So if you have a one-dimensional function, let us say consider f from R to R. which is f of x, which is given by f of x is equal to, let's say, sine x. Very simple function, very nice. What is f prime x?
Cos x.
That's just cos of x. But you see, f prime is also a function from R to R, right? So I can further differentiate this. I can again analyze whether this thing is here in this case, it's a trigonometric function. So it is infinitely differentiable is what we call it. We can differentiate it again to get f prime and the derivative of that and so on. In general, we denote it by fn. But what happens when you have a multivariable function? For simplicity, let's just take f from R2 to R. And let's take f of x comma y is equal to, say, sine of x1. Now, what we do have is either there is this function called the gradient of the function. I'm writing it as R2, but to write it as R2, you have to verify that all of these things exist. But since this is composition of a trigonometric function with the product of two scalar valued functions, it's a very well behaved function. So gradient of this makes sense. Gradient of f at x comma y. Sorry, gradient is a vector valued function, right? It has two components. Can you tell me what the components are?
Cos xy times y.
And what's the second component?
Cos xy times x.
Yeah. So this is just fx at xy. In general, it is fx at xy and fy at xy. Now, this is a vector valued function, but its components, these are again multivariable scalar valued functions, right? We have these two guys. In this particular case, we have fx of xy is y cos xy and fy of xy is x cos xy. If I just give you the functions y cos xy and x cos xy, you know how to take partial derivatives and directional derivatives and so on. So we can do the same partial derivative business for these functions fx and fy. Right? So I have something called fx, the x partial derivative of that, fx and the y partial derivative of this. Then I have this function fy, the x partial derivative of this, and fy, the y partial derivative of this. Right? I have four things. These are called the second order partial derivatives of f. Just like in the one-dimensional case, you don't really have two like different directions to work with. So you just have f, f prime, f double prime, and so on. But in the case of multivariable functions, you have different directions and different direction partial derivatives. And each of those is a scalar valued function whose partial derivatives you can again take, and you will get, in the case of two-dimensional two variable scalar valued functions, you'll have four different quantities, four different, once again, scalar valued functions, which are called the second order partial derivatives of it. A quick note on notation. This fx, the x partial derivative of f of x, is generally written as fxx, or this is just like when you write d square f by dt square for a function, for a one variable function in t. It's similar notation, or if you want to write it even more explicitly, it is written like this. All of these mean the same thing. What happens similarly for y, I'm not going to write it for y. And fx and y, there is a little bit of a avenue for confusion. So here this becomes del y del x. Why is this? This is because you're taking fx and then differentiating it in the direction of y. So first you have fx, which is del f by del x, and then you are differentiating that with respect to y. So here it comes in the order xy, but here it is written in the order of yx. Both of them mean that you differentiate first with respect to x and then with respect to y. Don't get confused with that. fxy and fyx are called mixed partial derivatives. Right, these, if you differentiate twice in the direction of x, that is not a mixed derivative. A mixed derivative is one in which you have distinct directions of taking the partial derivative. Then it is called a mixed partial derivative. Right, so this was for just the two-dimensional case. You can guess what happens for the n-dimensional case as well. For f from, let's say, Rn to R, I'm going to write Rn to R, but typically you will be considering a domain in Rn or a point in Rn around which the function is defined. Just for simplicity, I'm writing Rn to R. How many second order partial derivatives do you think exist? Any guesses?
And C2, sir.
This is one guess.
Power n.
Sorry, I couldn't hear.
The power n.
2 to the power n?
It's a lot.
So if it is NC2, then in the case R is equal to, n is equal to 2, you would have had 2C2. 2C2 is not the number of partial derivatives that you have. So that is not correct. Is it 2 to the n? So what will you be doing? You'll be taking f xi and xj. So this is probably where you thought it should be NC2 because you're making two choices. But it is not that you're making two distinct choices, right?
So it should be n square.
Yeah, n square is the right number. Because you have n choices for the first partial derivative and n choices for the second partial derivative. So in all, you have n square second order partial derivatives, out of which n square minus n of them are mixed partial derivatives. Now, let us maybe take an example to see. This is a routine computation, but let's just do it. Something like sine of x squared plus y squared. The fact that this is differentiable, the partial derivatives exist, all of this follows directly from composition laws and addition, multiplication, all of those things. I'm not going to write that down, but for a complete answer, you have to make sure that all of that happens first. So what is fx at xy? This time it will be 2x cos of x squared plus y squared. And fy is 2y cos of x squared plus y squared. Right. So when you have to differentiate only with respect to, as in a coordinate direction, that is the partial derivative, not the directional derivative, you just have to treat the other thing as a constant. So here you will treat y as a constant, and here you will treat x as a constant, and do the usual differentiation, and you get this expression for the partial derivatives, for the first order partial derivatives. For the second order partial derivatives, what is fxx This will be 2 times cos of x squared plus y squared minus is this what it is? Is this correct?
Yes.
Okay. And let's stay on the partial derivatives of fx itself. If I do with respect to y, I'll get 4xy. Yeah, if I make a computational error, please let me know. 2x minus sine and another 2x. Another 2y minus sine and 2y. Yeah, this is okay. What is fyx? At xy, I get a 2y, and then, so here you're, just to emphasize the point further, you're taking the partial derivative of 2y cos of x squared plus y squared in the direction of x, meaning you will be treating y as a constant and differentiating with respect to x. In this case, what happens is you have a 2y and derivative of cos of, as in partial derivative of cos of x squared plus y squared, which will give you minus sine times 2y, 2x. So totally you will get minus 4xy sine of x squared plus y squared. This is, yeah, fyx is dou by dou x of fy, which happens to be this. Now the other one is fyy at xy, for which you will get some expression like the first one. It will be 2 times cos of x squared plus y squared minus 2 y square, I believe, sine of x squared. So this is how you compute second order partial derivative. Now what you might have noticed, or if you have not, do it now, that fxy is the same as fyx, at least in this case. right? I have minus 4xy sine of x squared plus y squared and 4xy sine minus 4xy sine of x squared plus y squared for both the mixed partial derivatives. So is this because I've taken a very symmetric sort of function? It is interchanging x and y does not really change the function. So you sort of expect the mixed partial derivatives to be equal, right? So let's take another example where that might not be the case. Let's say x4 plus y squared plus e to the x or something like that. E to the x y squared, something like this. This is not really symmetric in x and y. If I differentiate with respect to x, I get 4x cubed plus y squared e to the xy squared. I'm not going to go into the details. By now, you should be comfortable with computing these partial derivatives. Can someone tell me what is fy of xy?
Two y plus e power xy square.
You will get 2y plus 2xy, right?
E power xy squared.
Yeah. So then the second order x derivative is 12 x squared plus y to the 4 e to the xy squared. Treat y as constant and differentiate. This is what you get. fxy will be differentiate fx with respect to y, which will give me 2y e to the xy square plus 2y cubed. Is this correct? There must be some x missing. Right? Is this correct? xy, yeah, it should be correct.
Yes.
And for the second order derivatives which begin with the differentiation with respect to y, we have the following. We'll have this first time is constant, so I'll just take y times e to the xy squared plus xy squared. Something like this, I believe. Yeah, man, that's what I actually wanted. Y will be 2 plus 2x is a constant, e to the xy squared plus 2 2x is out. We just have y, 2y with an x. Something like this. I might have missed some computations. If there is, you just correct it. But the important thing to note is that this and this are the same. Right? It's 2y e to the xy squared plus 2y cube x e to the xy squared. So this is where we have Claroux theorem. Not sure if I'm pronouncing the name correctly. I think it's pronounced as Claroux. If Let me write this statement just for the two variable case first. Is a scalar valued function. The second order. So what are the required conditions? To ensure that the mixed derivatives are equal. That is what Claroux theorem says. And the optimal conditions is that second order partial derivatives exist and are continuous continuous. When I say around, let me not write around. In a ball, around say A tilde, then fxy at A tilde is the same as fyx at A tilde. So even though there's a, sorry, is there a doubt?
Sir, what this order exactly denoting? Number of times you are derivating or
Number of times that you're differentiating.
okay, I thought of like variables.
No. Even for a multivariable, even for a function like this, fxy, or let's say fx1, x2, this is the second order partial.
Okay.
So typically you will have fxi, xj, I and j vary from 1 to n. So to see that this condition is essential, consider the following function. I think this is a function that works. Is the sound from the fan too distracting? Is it even audible?
No, sir.
Okay, cool then. I think this is the function. I'm not, yeah. For now, let me leave it as an exercise. Maybe towards the end of the session, if there is time, we'll revisit this. Check that. Second order partial derivatives. F are not continuous. They exist, but they're not continuous. And fxy partial derivatives of f, again, at the origin. It seems like away from the origin, it's a nicely behaved function, well behaved function, because it's just a rational function with denominator not vanishing. So away from the origin, everything is good. But at the origin, the second order partial derivatives of f are not continuous, and this is not equal to this. So this exist and are continuous is very important. And you can say that These two things
Sir,
are equal. The mixed, yes.
sir, is it reversible? I
What
mean,
do you mean?
uh, if this equation holds, does that guarantee their
No,
continuous?
that's a good question. I don't think it is. This seems like a weaker condition. To manufacture counter examples for that, I'll have to think a little bit more. If I can think of something, I'll let you know. But my gut feeling is that it is not. I'm pretty sure it's not. That if even if you have equality of partial derivatives, uh, right? Give me a few seconds. Maybe you can think of some example quickly. Maybe take this function. I think one of the functions that we had discussed, where I consider it to be equal to 1 on this parabola and 0 everywhere outside. For this, I think the partial derivatives will be identically 0. How? Oh, but then the partial mixed derivatives also will be equal. Mm, no, I cannot think of anything, but I'm almost sure that that is not true. The converse is not true. You can have a function which has equal mixed derivatives, but the second order partial derivatives are not continuous. Yeah, I'll think about it. Right now, I don't have a complete answer.
Sir,
Yeah,
what does this equation say as per the rate of change of the function?
it does not say anything about the rate of change of the function. It just says that the order in which you take the derivative does not matter uh, for well-behaved function. And later on, you'll see that that implies some symmetry on the Hessian matrix, which actually captures the entire picture of the second order differentiation. If we get to this point, you'll probably see, if we get to this last point, you'll probably see what I'm trying to say. But let's postpone that for later. Because second order derivative does not capture the rate of change of the function. It captures the rate of change of the function. It's like acceleration, right? It's not speed or velocity. So this is the second order change. So what it is saying is that the rate of change of the x derivative with respect to the y derivative is the same as rate of change of y derivative with respect to the x derivative. Not about the rate of change of the function itself. So with all of this in hand, we are in a position to define what a Hessian of a matrix is. Hessian matrix of a function. It is denoted HF is a square matrix. HF at xy. So let me just call this x tilde. This would be fxx, x tilde, fxy, x tilde, fyx, fy. Now I don't know. Wait, let me be more careful. I think this is fxy over here and fyx over. This is 1, 2. This is 1, 1. No, this is 1, 2. 2, 1, 2, 2. Now the earlier thing is right, I think. Yeah. So this is a matrix, as we saw earlier, that if I have a scalar valued function which is defined on that's with n variables on the domain, then we have n square many partial order, second order partial derivatives. Now, if I put them all in a matrix, that is called the Hessian of the matrix, and that is the notion of second order derivative of a scalar valued function. So this captures the total, some sort of total second order derivative. Most of the time, I mean, we don't worry about whether it is xy or yx because the functions that we work with, typically we would want it to satisfy the hypothesis of Clairaut's theorem, wherein it doesn't matter if I write it as xy or yx because this becomes a symmetric matrix in a sense that there is there is reflection symmetry across the diagonal. You have fxx, fyy, and so on, even if you have multivariable functions. And this entry will be equal to this. More generally, if I have an n-dimensional multivariable function, and I think HS. So let me just write it this way. The ijth entry of the Hessian matrix is nothing but xi, xj. This is correct. If it is xy, xj, then here this will be L square f5. This is 2, 1. Right? This is x2. X2 is y, x. So this is xy. Yeah. Just verify what the correct notion is. I think this is correct. At least this is consistent with this. So it is the ijth entry is given by del 2f, del xi, del xj. In the case of multivariable functions, you have n variables, which we are calling x1, x2, so on up to xn. And I can take any variable first, take the partial derivative with respect to that, and then follow it up with the partial derivative of that, of the partial derivative that we got in another direction. So there are two steps. First you do j, then you do I. That gives you the ijth entry. Again, in most cases, Clairaut's theorem. So Clairaut's theorem here I've stated again only for R2, but the same thing is valid for Rn. In fact, I can just change this to Rn, and yeah, there here I'll have to say fxi, fxj. Let me keep it as R2, but know that it is true for n-dimensional multivariable scalar valued functions as well. Same thing, the condition that you have to check is again the same. Do the partial derivatives exist at the point, and are they continuous? Then the mixed partial derivatives will be equal. And the Hessian matrix will become a symmetric matrix. You'll have f x11, x1, 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 f x2, x2, and so on. f x n f, fx and xn. These are the diagonal entries, and the general off diagonal entry will be fxj fxi. This is the ijth entry. So there's a switch, you see. So when I write it as in terms of the derivatives, if I have ij, then I'll have a ji when I write it in this compact notation. So these are the off diagonal entries. So this is the Hessian matrix. Now, why do we even go into this technical thing? Is the second derivative test. If you just have to compute the Hessian matrix and you want examples for that, you just again consider these examples and put these all in a matrix form. This is why I did fxx, fxy, and then fyx and fyy, because that is generally how it is written. And you can see as soon as you compute the second order partial derivatives, you have your Hessian matrix. It's just putting them all together in a box. But now we'll see an application. Was there a doubt?
Sure.
Yes.
And I don't know if it's appropriate or not. How do we
Yes.
derivate a mod function?
You can differentiate a mod function only when there are no sharp edges, right? Otherwise, the derivative does not exist. So on the part where there is the one-dimensional mod function. Over here, it is pretty much your standard. It's either x or minus x. You can differentiate it. But over here, there is no derivative. So similarly, if you have the two-dimensional, say mod x plus mod y, it is this prism-like thing. What a bad diagram. Let me just draw that diagram. It's like this. It's something like this. And it goes further up. Right. On all these points, you cannot differentiate it because, see, as soon as you can differentiate it, you will get what is called a tangent hyperplane and all that. You can see that on all these points, on all these corners that have been drawn, actually, you cannot differentiate the function, right? And if you write down the equation and try to find the limit, the first principles definition, you'll see why you cannot differentiate. So the derivative of the function does not exist in that case.
Sir, when I Google the same, it says x by mod x, d by dx of mod x is equal to x by mod x.
If you have this, our function is this, yeah. I can write mod x as x minus x. X greater than or equal to 0, or x less than or equal to 0, it's minus x. Now the differential of this is 1 and minus 1 on x greater than 0 and x less than 0. At 0, it is not defined. So this can be written as x by mod x. You can combine these two to write x by mod x. Why? Because if x is positive, x by mod x becomes 1. If x is negative, x by mod x becomes minus 1. It becomes x by minus x. So the closed form expression for the differential of the mod x function when x is not equal to 0 is x by mod x. That is fine. But its derivative at x is equal to 0 does not exist. Right.
At the point other than the origin, it is differentiable, right?
Yes. There it is just 1 or minus 1, depending on x is positive or negative. And I can reformulate it as x by mod x. Because for x positive, mod x is just x. So it becomes x by x, which is 1. For x negative, mod x is minus x. So x by mod x becomes x by minus x, which is minus 1. So that's the derivative of,
Thank you.
yeah, mod x, but at 0 it does not exist. You can have similar expressions for two-dimensional modulus function like mod x plus mod y as well. On places where it is differentiable, you can do it and you can get an expression for it. But there are lots of points where it is not differentiable, where the tangent hyperplane does not exist, or in other words, the derivative does not exist. Now let's go to second order test. For explain some sort of a recap in some sense is, can someone tell me what the local extrema? Okay, this is local extrema test using second order derivatives is for a one variable function.
Critical point and either a local minimum or local maximum.
So you say this happens,
Critical point exists.
then if f prime x is positive, what happens? Sorry, f double. What is the missing thing?
Minimum.
And of course, there's this guy. Do you say it's not conclusive or it's a saddle point? Or you want to remember that case? Right, there is not necessarily a saddle point. There is no saddle in one dimension. So, yeah, even if you have functions like f of x is equal to x cube, that doesn't have a minimum or maximum at x is equal to 0. And I would not like to call it a saddle point. Let's say just that the test is not conclusive. So what about R2 to R? You know the notion of a critical point. Let us say this is a point where this partial derivatives, second order partial derivatives. I need second order partial derivatives, but first of all, to call it a critical point, what is the equivalent notion of this condition? What is condition 1 in the multivariable case?
The gradient has to be 0.
Okay, let's just keep it. Gradient is 0. What do I mean by it is 0? Gradient is a vector. It's a 0 vector, which means equivalently fx at a tilde is 0 and fy at a tilde also is 0. Now that takes care of the first check, that it is a critical point, and assume that all of your second order partial derivatives exist and are continuous. How do we formulate this condition? It so happens that this is the formulation. First, let us just understand what it is trying to say, and then let us see. Then maybe towards the end, let us see what actually happens. So for the local minimum, over here you had positivity of the second order derivative. But here you need the determinant has to be positive and the first entry, the XX entry, has to be positive. In that case, you will have a local minimum. The second condition is if you have this, then this is the local maximum. These are both cases when determinant of the Hessian has to be, when the determinant of the Hessian is greater than 0. Now the other case, one is the determinant of the Hessian is less than 0, then this is a saddle point. I think saddle was explained in the last session. You will have the function behaving something like this. You have the function behaving something like this. Let's say, yeah, something like this. So along this direction, say, in this direction, it will be a minimum, but then in this direction, it will be a maximum, right? So this is what is the saddle point. There are two directions, one along which the function behaves like a minimum, and another along which, by this direction, I hope you understand what I mean. It is this direction. As you move, say, into the frame of the screen. So along that direction, your value is, by value again, I mean, say in some Z coordinate in an appropriate graph. So you see that this value is the maximum for that, for this curve, and this value is the minimum for this curve. So this is what is meant by a saddle point. And if determinant of the Hessian is negative, this is what we can conclude. And the last case is the determinant of the Hessian is 0, then the test is inconclusive. So are there any doubts about the conditions? It's like, it's just a straightforward statement, but first thing you have to do is check where the gradient vanishes. And for those points, you have to check what the determinant of the Hessian looks like. And if it is 0, then you cannot do anything. If the determinant is negative, then it's a saddle point. If it is positive, then you'll have to look at the first entry of the Hessian matrix. Depending on whether it is positive or negative, it becomes the local minima or maxima, respectively. So the same sort of behavior is seen over here. Here you have the Hessian. If you want to really talk about the Hessian, it's just a 1x1 matrix, right? So the determinant of it being, well, determinant of it less than 0 is not a direct analog of this thing. But the first entry itself being less than 0 or more than 0, that points it to being local minima or maxima. If you want to know, if you want to remember what is the behavior like when it is minimum and maximum, you can look at the same thing. The second derivative being positive implies minimum in the one variable case. Similarly, the first entry of the Hessian matrix being positive points it to being a local minimum in this case as well. Now, the only new thing is the saddle, where if your determinant is negative, then you have a saddle. And if determinant is zero, then the test is incomplete. That is also similar to the earlier. So yeah, that's that. Let's take up an example, maybe the same example. Will it be too complicated to take this up again? Let's see. Hi.
So
Yeah.
at saddle point, the function will get decreased, right? So that is why for determinant being
The
less
saddle
than
point
zero,
is
it
a
is
point
saddle.
where, could you come again? I missed some of what you were saying.
At saddle point, the function will start decreasing, right? So that is why when determinant is zero, it
No,
starts
it
saddle.
no, determinant is zero is not a saddle point. The test is inconclusive. When the
When
determinant is
determinant is
negative, it's
less
a
than
saddle. Yeah. So, and it is not like the function starts becoming uh, starts increasing or starts decreasing. That's the point of the saddle point. There are directions in which it sees a dip. There are directions in which there is a increasing behavior. There are directions in which there are decreasing behavior. Like these two red lines that I've drawn on the surface of the uh, let's call it the graph of some function. I don't know the exact formula for what uh, would give this as the graph, but if you have a function whose graph is this, do you not see that there are two directions? One in which it is a minimum and one in which it is a maximum. You can see that, right? In this direction, it's a minimum, and in this direction, it's a maximum. Do you see that? Hopefully, you do. Is this diagram clear or not? Like what I'm trying to show over here?
Yes, sir.
Yeah. Now, if I look at the critical points of this function, is it even easy to analyze? I don't know. Let's see. I want both fx and fy to be to vanish, right? So one of the obvious points is the origin, where x is equal to 0 and y is equal to 0. Both are both will ensure that fx and fy both are 0. So critical point, or you have the origin itself. And then there is another family of points. What are these points? The points for which x square plus y square is an odd multiple of pi by 2. Something like this. Right? These are your critical points. Does everyone understand why these are the critical points? Or should I explain it again?
Yes.
Yes or no?
Yes.
Yes, sir.
Is this clear? Yeah. Okay, cool. I want either cos of x square plus y square to be 0 or the coefficients to be 0. So these are the critical points. Now, what does the Hessian matrix look like? The Hessian matrix has fxx to be equal to this. The general expression of it,
Sir,
you can write it down. Yes, I think this is it.
I think there are some few more critical points, isn't it, sir?
What are the others?
Pi. See, when x and y are 0, it's 0 means when x square plus y square is equal to pi, then also
X square plus y square equal to pi gives me just this will not be 0. This will not
uh,
necessarily be 0.
mhm.
I want both of them to be 0. So
Okay.
x square plus y square has to be an odd multiple of pi by 2, which will make the cos of that to be 0. Or I want both of the coefficients to be 0, which happens only at the origin. So
Sir,
your critical point,
when x and y are zeros, the
yes,
cos 0 is 1, sir.
yes, but
Then,
this itself is 0, right?
oh, okay. Sorry,
It's
sorry, sir.
2x times.
No, yeah, I
So,
saw. I understood.
yeah. So your critical points are the origin, then you have a circle at r is equal to pi by 2. This is actually only positive multiples, so you can just call it this. And your critical points come in circles. Right? This is like r. By r, I mean the length of the vector. So this is the circle of radius pi by 2, circle of radius 3 pi by 2, and so on. The general expression of the
Sir,
Hessian, if you want to write it down, but I will calculate only for the critical points. Yeah,
n can be 0 also, right?
yeah, n could be 0. Yeah. Now, what is Hessian of f at 0? Now, this is the easier thing to do. So if I put 0, 0, this will give me 2. This will give me 0. This will give me 0. And this will give me 2. So it's 2002. At any point, if you want me to repeat anything, let me know. I'll be skipping through most computations, which are straightforward. So once you have this, the first thing you have to check is what is determinant of the Hessian at the given point, and that is equal to 4. Right? Now we go to a checklist. Determinant is positive. I'll have to look at what is the first entry. And if the first entry is 2, that is at xx at 0, 0 is 2. These two together imply that 0, 0 is a this is greater than 0. Greater than 0 is
Local
minimum.
minimum, sir.
This is one set of points. Now, if I have x square plus y square is equal to 2n plus 1 pi by 2, that is the next set of points that I have to look at. For an appropriate n. What does this come out to be? This will be something like minus 4 x naught square. I'll just keep it as x naught square because I don't really know what the value is, but it's a positive number. Probably that will suffice. I'm just leaving it at that because I don't want to deal with all the general expression of that. And sine of x square plus y square will be minus 1 to the n. Say for n is equal to 0, it becomes plus 1. Yeah, for n is equal to 1, it becomes minus 1. Yes, so it is this, and this becomes minus 4 x naught y naught. Let x naught y naught be some point with these values is what I'm saying. It's again minus 1 to the n. And here I'll have minus 4 y naught square minus 1 to the n. Everything has a minus 1 to the n. So the Hessian of f at some x naught y naught, which satisfies this condition, the thing turns out to be 4x naught square minus 1 to the n plus 1, 4x naught y naught minus 1 to the n plus 1. Again, 4x naught y naught. Right? Is there any confusion about how I got the Hessian? Okay. If not, I'll go ahead. So this is nothing but 4 into minus 1 to the n plus 1 x naught square y naught x naught. Fortunately, this will be 0. If my calculations are not wrong, this will give me determinant of Hessian is 0. And then you cannot conclude. But if you actually go to GeoGebra and draw the graph, you'll see that these points do actually correspond to some minima or maxima, because you can see that f is sine of r, right? This is like sine of r. So it should be like waves in the radial direction. It should look like this. And these points where it is, when r is pi by 2, when you have odd multiples of, as in when you have, what do you call it? 2 pi plus pi by 2 kind of terms, 2n pi plus pi by 2, they should be maxima, and 2n pi minus pi by 2, they should be minima. But this test does not reflect it. But that does not mean that that is not a maxima or a minima. So what the test says is that If these conditions are met, then you can conclude that this is a local minima or maximum. But the converse is not true, right? You can have this. This test is inconclusive means there could be functions for which the determinant is zero, but actually a minima or a maxima is attained at that point. Or there could be a function which behaves weirdly and maxima could be attained or could not be attained. That cannot be detected by this. So if this is the case, then you're out of luck. Then you will have to try other things. There are no other things discussed in the context of this course, but there are other ideas to detect minima and maxima of functions. So hopefully there's no computational error in this and the determinant is actually zero. Let me just quickly glance one more time. I don't feel like there is anything wrong. Yeah, everything has a sign of x squared plus y squared, so that gives me a minus 1 to the n, and yeah, that kills everything. So yeah, go back and check if this is correct. If not, if this is not zero, and if I've made a mistake, then you will see that the minima will be pointed out by this condition and the maxima will be pointed out by this condition. Once again, draw the graph on GeoGebra or whatever graphing tool that you would like to use and see how the function behaves. It behaves radially symmetrically in the sense that all the values at every circle around the center, they are the same. So it goes in waves starting from the origin. So that you can check. So this is one application of the Hessian, and it gives you the notion of a second derivative test, which is somewhat similar to the one variable case. Now this is for a function which is from a two-dimensional space to one-dimensional space. That's a two-variable scalar valued function. But what about more variables? Right? Because this specifically says this is only for two-dimensional case. This thing is not can be generalized. This is, let me write it over here, only for two-dimensional case. Now, why
Sir,
is this only?
you mean the Hessian matrix, sir?
No, the second derivative test using the Hessian matrix, as in these conditions, like determinant of the Hessian is greater than zero and the first entry is positive, then A is a local minimum. That statement is valid only for functions from R2 to R or domain in R2 to R.
Oh,
So
is it? Okay.
yes, yeah. And for R3, we have the following. And we'll stop at R3 and you'll see why. Now the same conditions will all the regularity conditions will be assumed. You have a function defined on a domain. A is a critical point. First and second order partial derivatives exist and are continuous. All of these things I'm not going to write down in R3. Once again, I keep saying R3, but this is valid on any domain in R3 also. A is in R3 is a point where F satisfies all those conditions. For the full list of conditions, refer to the lecture videos or the notes. I'm not going to write everything over here. And nabla f at A is zero. This is a critical point. Now you start out with the critical point and determine the nature of the critical point. That is the second derivative test. So that is always there. Now, just for three-dimensional case, you see how many conditions, how many additional conditions you have. You have this has to be 0. This has to be 0. Sorry, positive. This also has to be positive, and determinant of Hessian of A tilde, Hessian of F at A tilde. This is also positive. Implies, put an if over there, is a local minimum. If this is negative, this is positive, and this is negative, implies there is a local maximum. Then you have determinant of this is not 0, and 1 and 2 do not hold. One, actually I should write 1 or 2 do not hold, implies A is a saddle point. And finally, if determinant of the Hessian is 0, test is inconclusive.
Sir, so do we have R3 to R also in syllabus and they come for the exam, sir?
I believe so, yes. So this seems like a lot of conditions, yeah? So how do I, there is a easier way to remember it. When you're writing the Hessian of a function at A tilde, I'll skip the A tilde. I'll just write the whole thing. You have fxx, fxy, it might be fyx, but in these conditions that come over here, they guarantee that this is a symmetric matrix. So it doesn't really matter. But otherwise, you need to be careful about what you write. Yx, yy. Wait. No. X, Z, Yx, yy, yz. Then you have Zx, Zy, and Zz. Right, this is the Hessian. What are the conditions? Take, for example, look at this first condition. F of xx is just this first minor. Like just start with the first element, and then you take the bigger box that contains fxx, fxy, fyx, and fyy. What is fxx, fyy minus fxy whole square? Because these two are equal. This is actually the determinant of this slightly bigger box. You can think of fxx also as the determinant of the smallest box. You have this determinant of, let's say, fxx to be greater than 0. Then you have determinant of fxx, fxy, fyx, fyy. This also has to be greater than 0. Then you have the whole thing, the determinant of the Hessian at the point. I'm leaving out this at the point, but you have to evaluate it at a particular point where you are a particular critical point. So you take this 1 cross 1, then you take this 2 cross 2, and then you take the whole 3 cross 3. If all of these are positive determinant matrices, then it is local minimum. But for local maximum, what happens is minus plus minus. So you look at these three gradually increasing size of matrices, plus 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 implies local minimum, minus, is it minus plus minus, or yeah, it's minus plus minus. This is one way to remember. Instead of having all of these things, you look at this Hessian matrix and you look at the gradually increasing matrices. In gradually start out with the 1 cross 1 element, and then you increase one by one size, increase by the whole thing. And this is sort of how it is generalized to n dimensions, but you'll have to take appropriate signs and the expressions become even more complicated. So this is where we stop, and we just say plus 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 points to local minimum, minus plus minus points to local maximum. Any other sign combination implies saddle point, provided the determinant is non-zero. This guy is non-zero. The last entry is non-zero. The saddle point, anything zero implies inconclusive. This is a slightly easier way to remember these conditions. But nonetheless, all of this does point to the fact that Hessian does capture some sort of minima maxima. I mean, it points to certain minima maxima, may not be always. And in fact, you will see many times it is a determinant Hessian f is 0 is not a small class of functions, whatever small means. So, but in any case, this is one way to look at it. That is what is important to note. And that brings us to the end of the thing. And since we do have time, I will talk about this. Yeah, I have covered whatever I needed to cover. Do you want me to do an example of a three variable function, or would you want me to give that interpretation? Please just let me know.
Let's do one three variable problem. Sir.
Okay. Do you have any favorite function?
X y by x square plus y
Don't
square.
do by. So there, actually, your partial derivatives are not continuous, right? They're not. It's the
Yeah.
second order derivatives. There your partial derivatives are not continuous, so that I cannot use. Here, this satisfies these regularity conditions is that partial derivatives of second order exist and are continuous in a ball around the point. So let us take a simpler example. Something like this. Xy plus yz, zx. I don't know if this will be easy, but let's see. So fx is
I plus z.
that's a constant. It'll be just y plus. Oh, I don't think this will be easy. How will I even determine critical points of this? Let's see. If you cannot determine critical points of this, we'll skip the sign and just do xy plus yz plus zx. Of course, origin is a critical point because you'll have, and that is the only critical point other than the level set of this thing where xy plus yz plus zx is equal to 2n plus 1 pi by 2. Does this have a solution? It should have solutions. You can put y is equal to 0 and then you can, I don't know what the solution set to this is, but maybe it doesn't matter. Let's see. The critical points are 0, 0, 0 and x, y, z such that xy plus yz plus zx is equal to 2n plus 1 pi by 2. Right now, fxx, this is a nice function, so I'll get a symmetric matrix. So I just need to do 6 of the second order derivatives. The other 3 come for free. Once again, I'll drop the of xyz wherever it is not required. Y plus z is constant, so I'll have minus sine. I suspect I'll get something similar to the last times thing only. This will be just this. At any point, if you want to know, if you want me to explain a bit more, let me know. Here I'm just computing the partial derivatives, second order partial derivatives, taking the first order partial derivatives and then differentiating them with respect to the second one. So here I'll get a this plus it becomes minus y plus z the whole square. Will it be y plus z the whole square? No. Y plus z into x plus z. Sine of that term x z will be, there's a pattern x z, right? You will have a y plus z and x plus y sine of that guy. I'll skip stuff f y y. One, two, three, four. X, Y, X, Z, Y, Z I need. That will also be cos of this thing minus y plus x plus z sine of that expression. And the final thing is sine of that expression. Wherever the brackets have not been completed, it's xy plus yz plus zx. Now at the origin, Hessian of f at the origin. That is one of the critical points. So we need to compute what that is. What happens to this guy? This is 0. This is 0. This is 0. And the off diagonal entries are this is 0. This is 1. Let's say this is also 1. This is also 1. So you will have the Hessian to be this. And what's the determinant of the Hessian? So first of all, but determinant I have to verify first anyway. Wait, in order to verify whether it is a saddle point or not, first I have to see whether the determinant is 0 or non-zero. What is the determinant? Can someone quickly compute? Minus 1 into minus 1, 1 into 1. This is 2. Right? Is that correct?
Yes, sir.
Yes.
Okay. The determinant is 2. Then what case do we land in? Determinant is not 0, but you don't have any sign for the first entry. So it's not case 1 or case 2. It's not a plus minus plus. It's something like a 0 something, 0 star 2, right? So it's like 0 star plus. So that does not fall in any of these cases. It doesn't fall in this case. So it's a saddle point. Now to verify it's a saddle point, as in to actually find the directions in which there is increase and there is decrease, that will be more difficult because of the nature of the function and how many computations are involved. Most of the times, it might be computationally heavy, but conceptually, the same thing keeps happening. You just have to compute the second order derivatives, put them in the matrix, evaluate it only at points where it is relevant. In this case, it is the origin and the points where this thing happens. So even though all of these expressions might look big and nasty, as soon as I have this condition xy plus yz plus zx equal to 2n plus 1 pi by 2, everything gets simplified. So cos terms will vanish and the sine terms will uh, become 1 or minus 1, depending on whether it is 2n plus pi by 2 or 2n pi minus pi by 2. It will become plus 1 or minus 1 and you'll get corresponding signs. I don't know what happens to the determinant. Maybe take it as an exercise. I suppose the procedure is clear and let us not waste time on the details.
Sir, we will take something in the AQ, sir, activity questions. So that we know, we get realistic problem, whether it is
Okay.
complex or simple, we know that, okay,
Okay.
it is something that we have to solve.
Okay, all right. Which one do you suggest?
Sir,
Yes.
is this the one you are talking about, the full derivative? Is this matrix?
Hessian is not. No. Hessian is not. The derivative is for a scalar valued function, it is just the gradient. For a vector valued function, it becomes an m cross n matrix with the partial derivatives. But the existence of that itself does not imply differentiability. Differentiability you will see in the next session. As in this, that is the only topic that is actually left to cover. So that will be taken care of by someone else. I'll not go into that because maybe we don't have time to cover
In
that.
week 12,
Sorry?
in the next week or this week?
In the next session, it should be. It is a week 11 content itself. What it means for a multivariable function to be differentiable. So we have talked about partial derivatives, directional derivatives, and all that, but we have not said that this is the condition which is a defining condition for a scalar valued function to be differentiable. So there is another limit that exists similar to the case of one variable. So we take the condition in the one variable function case and then we generalize it to the multivariable case, multivariable scalar valued case, and then multivariable vector valued case, It's just that every component has to be. All of that will be taken care of. Let me not confuse you by just saying stuff, but this matrix, the Hessian matrix, is the notion of acceleration. It is not the notion of velocity, or it is not the first derivative, it's the second derivative.
So do we
And the
get any questions?
existence, sorry,
Do we get any questions about that differentiability?
I don't know about that. That is, it is a topic in week 11, so I believe there should be some question. That is also a topic that needs to be read and covered. Yeah. So, is there any particular AQ question that you would like to take up, or
Yeah, there is one.
could you speak louder? I
Yeah,
cannot hear you.
there's one. 2x cube minus 3x squared y.
Is it there in the set, or
Yeah, it is 11.2 fifth question. I'm just selecting
7.2?
something at random. Yeah,
Okay,
fifth question.
thanks. Hmm. Level 2, the first question.
The fifth one.
Yeah, the fifth one, the level 2 first one. Yeah, yeah. If it is polynomial and it's not doesn't have any trigonometric thing, things will die. As in, it will be polynomial itself of lesser degree. So polynomial equations are easier to solve. So this is one of the questions. So it says find choose the correct statements. One of the thing is F has 3 critical points. Let's just see what critical points does F have. So you need to see Fx, Fy, or the gradient of F at x comma y. This is 6x squared minus 6xy. So to see what are the critical points of F, we have to equate this vector to the zero vector, right? So I have two
Are you
equations.
sharing something?
Oh, is it not being shared?
Uh, yeah, I can just see one blank page.
Is it not visible to anyone else?
See,
Or
see.
No, sir, it is visible to me.
Oh, I'm sorry. That must be mine.
yeah, could you refresh? Is it visible now?
Yes, yes.
Yeah. Okay. To compute the critical points of this, we need this to be equal to 0 as well as this to be equal to 0. So we are on the line or on the parabola. X square is equal to minus 2y. Yeah. So this gives me that. And if I put this back in this, what I get is 6x squared plus 12, not 12. 2y is minus x squared. So minus plus x cube. This is a cubic equation. Unfortunately, we have one easy solution, and I divide. So this gives me x is equal to 0. That is one possible solution. Or I have x squared plus 2x minus 8 is equal to 0. And this is what? X plus 4 into x minus 2. And corresponding y values you'll get. So the critical points are 0, 0, -4, and
-8, -2.
thank you, -8, and then
2 -2.
2 minus. Yeah, these are the critical points, and that one of the questions is check if f has 3 critical points, and that's correct. And then let us determine the behavior of these critical points. To do that, we need fxx, all the second order derivatives. There are 4 of them. This is fx, this is fy. So let me write it over here itself. Fxx is 12x minus 6y minus 24. Fxy is minus 6x. Note that if you do fy and take the differential with respect to x also, you'll just get minus 6x. And fyy is minus 6, right? Now Hessian of f at the general point x comma y is a 2 cross 2 matrix with 12x minus 6y minus 24, is it? Yeah. And minus 6x and minus 6. If the computations are right, they should be it. And you look at Hessian at 0, 0. This will be minus 24, 0, 0, minus 6. The determinant is a positive number. It's positive. And fxx at 0, 0 is negative. So what does this mean?
It's a local maximum.
This implies
Local maximum.
at 0. Similarly, you can analyze the other points and do the thing. And there is another question which says f has a global minimum. Now that you'll have to be more careful about. The nature of this function. I don't even know how you would directly go about it. Has anyone done the last part of that problem to determine whether or not f has a global minimum?
Actually, I did it, sir, but F has global minimum. I did not get.
Yes.
I did not get anything. Actually, I think the no, sir. I did not get any global minimum.
You'll have to determine the behavior of F.
Global minimum.
What happens with the other critical points? What about -4, -8, and 2, -2? What are the what is the nature
So
of those
-4,
critical points?
-8, -4, -8 is a saddle point, sir. I
Okay,
did that.
okay. And 2, -2?
Two minus two was. I think it's something. It's a maximum or minimum, sir. Actually, I don't have the workout in front of me.
Okay, okay, okay. Okay, no, I'm just thinking what is the easiest way to determine whether F has a global minimum? You could take things like the line x is equal to y. What happens there?
Sir, we have already did dou f by dou x and dou f by dou y, and we have got all the critical points now, sir. So those critical
No, but
points, uh,
that does not guarantee that the global minimum exists or not. The global minimum might be outside your critical points also, as in you cannot say whether a global minimum exists or not. Now, if it exists, it will be one of the critical points. But take, for example, the
correct, sir. Your statement was right. If f has a global
yes,
minimum, then it should be one of the
yes,
critical points.
yes,
So the what I did is I found these the three critical points, and I found the
yes.
values of all these three critical points, and
Okay.
there was nothing like a global minimum that I observed.
So you're saying it does not have a global minimum.
Yeah.
No, but one of the three has to be a minimum, right?
No, sir. The function will go direct to negative infinity to positive infinity. No, sir. In that case, you may not have a. I mean, minimum.
No, 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 no. I'm not understanding your line of attack. So could you repeat that?
Sorry, sir. Actually, I switched off the fan.
No, that's okay.
No,
You
no.
repeat what you said.
No, what I was saying is I found these
Yeah.
three critical points, sir, and the three critical points I found those the values, and
Okay.
actually the global minimum, because actually this has a cube,
Okay.
right,
Let's
sir?
see.
Because it has the cube, it will be minus
Mhm.
infinity to plus infinity, sir. Function value.
I think you'll have to justify it a little better than that. Uh, so what I was thinking is, okay, F has a maximum, local maximum over here, and it has a saddle-like behavior somewhere at 4, -8 or something. But how are you concluding that this implies it has no global minimum? See, I'll tell you what I'm thinking, and that is a complete argument, but I don't know if that is the easiest way to go about it. Consider the line x is equal to y in the xy plane. So f of x comma x, this will be 2x cube minus 3x cube minus 12x square minus
3x square.
3x square. Right. So this is minus x cube minus 15x square. Now, as x approaches infinity, or if I take larger and larger x, I get
Yeah.
smaller and smaller f of x comma x. So along this line itself, I don't have a minimum. Like it can go lower than any number that you want, right? So f does not have a global minimum. So this is a complete argument. But I don't know if this because this x equal to y line just happened to work for me in this case. There might be better or I don't know if there is a an algorithm to go about doing this. But this definitely works. Picking out curves and saying that along those curves you can always pick points which you want to be as small as you want is a complete argument to say that it does not have a global minimum. Do you understand what I'm saying?
No, I did not, sir.
This part, did you understand?
X equal to y.
So
Okay.
I'm traveling. So looking this graph will be some surface, right, in R3.
Uh-huh. Uh-huh.
This is say X, this is Y, and this is Z, and this is
Uh-huh.
the graph of f of x, y.
Yeah.
And if I move along the line x is equal to y, what
Uh-huh.
I'm analyzing the behavior of the function as I move along this line, right? And it happens to be minus x cubed minus 15x squared.
Okay.
Now I can choose x.
If x is infinity, goes to infinity, z value goes to minus infinity, sir.
Yes, that's what I'm saying. So you can always choose a large enough x to make your f of x comma x as small as you want. Right. So this surface will actually go down like this at some point. Now, what does it mean to have a global minimum? So there is no point on the plane at which so f has a global minimum implies there exists some number m such that f of x comma y is always greater than or equal to m, right?
Correct.
Now, whatever m I choose, I know I can take a large enough x such that this equation is violated,
Correct.
right? So then this cannot happen. F does not have a global. So if it had a global minimum, there would be a minimum number. That minimum number I'm calling m. But by increasing x, by increasing x, I can decrease this as much as I want. So
Correct.
there is no end to this. Like it's a bottomless surface. Right. So this is a fair argument, but I'm not. No, I don't know if it's the best way to do it. But that's okay.
Sir, what I'm not actually understanding is
Yes.
we have got three critical points. We can find
Right.
the function value at all these three critical points. And
Yes.
okay, now if we can just find one point which is less than these three values, our job is done, no, sir.
Yes. That also works.
That's what I was saying actually. I mean,
Okay.
I
Okay.
found the values, function values at all these three, and
Okay.
obviously there are actually much bigger values on the lower side that I mean, much smaller values that we can go
Okay.
on
Okay.
the lower side
Okay.
to
Okay.
compare to all these three, and so there is no
Okay. Yeah.
global
Yeah.
minimum.
Yes. 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 That works. That works.
Okay, sir. Yeah, that's how I did it, sir. Okay.
Yeah. Okay. Are there other doubts? Yeah. To summarize, most of what we discussed today was how to use second order, how to compute second order partial derivatives, and how to use those second order partial derivatives to deduce extreme points, local extreme points of a given two variable or three variable function. Most of the times you'll be dealing with two variable functions itself. But for three variables also there is an algorithm. The increase in the number of variables does imply increase in complexity of computations. But the philosophy is quite similar, and the interpretation of these conditions is not something I can get into now because of lack of time. The only thing that remains in week 11 is differentiability of multivariable functions, which will be taken up in the next session. And yeah, if you have any doubts, please stay back. Otherwise, feel free to leave.
Sir, when will be next session?
I am not sure. Probably Karthik will announce it. I'm not sure.
Oh, the thing is that tomorrow is our deadline
Oh,
for week
oh,
11.
okay. There will be a session tomorrow, I think, but that will be a TA session. And yeah, probably that topic I'll ask them to cover it then, if that helps. And it's a small topic, so yeah, I think they'll cover it. Even in the AQ, there's just one question. It's like just check which of the functions is differentiable. It's just a limit evaluation. Go through the props lecture videos. Those are it's a short video also, I think, where there's just one definition. So yeah, you can quickly go through that and answer the required question. In any case, if there is any session tomorrow, I'll let the TAs know that uh, they have. I'll just tell them to cover that last. Okay. Are there any other questions? Is everything explained so far clear?
Yes. Yes, sir.
Okay then. I think
Thank you, sir. Thank you, sir.
yeah.
Thank you, sir.
Thank you, sir.
No problem.